Okay, hi everyone. Still continuing section 1.4, and now we are on the topic of one-sided limits. So let's kind of read this leading question here. What if a function changes values depending on whether the x approaches from the left or from the right? So looking at the left side of that x and right side of that x. So this brings in this definition of one-sided limit. So left, you're going to have two types of limits, a left hand and a right hand. So let's read through the left hand. So we write the limit as x approaches a. You'll notice some type of minus sign right there. And what that means is you're coming from the left. So we'll say something like, if it says x approaches a and it has a minus sign up top, that means from the left. Okay, let's keep reading. So we say the limit of x approaches a from the left is equal to L if we can make values of x arbitrarily close to L by taking x sufficiently close to A and it is less than A, meaning all x values less than A, coming from the left side. Okay, so that's a left side limit. Let's look at the right side limit now. So right side, if x approaches A and you see a plus sign here, right? You see the plus sign above on the A, that means you're coming from the right. So if it says x approaches A with the plus means from the right. Okay. So pretty similar statement. Limit of x approaches f of x approaches x from the right is equal to L if we can make the values of f arbitrarily close to L by taking x sufficiently close to A and x is greater than A, meaning values greater than A, meaning from the right side. Think of it as like a number line. Okay. So let's go ahead and look at an example. Okay. So a function with a jump. You see this function here. This is called a jump. You're jumping from this guy to that guy at 2. But okay, so let's go ahead and check it out. So we want to find if this limit exists. So we're looking at it as x approaches 2 and it has a minus there, right? Has a minus. So where were you approaching from? The left. Okay, so we're checking out the limit as we approach 2 from the left. So here is 2, right? I'm going to highlight it just to show like that's what we're checking out. So if I'm approaching 2 from the left, right? What value am I getting close to? I'm approaching it from the left. Here's x equals 2. What value am I at? Looks like 4. Okay. So as I'm approaching 2 from the left, my function is going to 4. So what I would say here is 4. Okay. Likewise, let's check out the next one. So this one, we're approaching 2, has a plus sign. So that means from the right. Okay. So we're approaching 2 from the right. I'm coming this way from the right. And what does that equal? Well, that's a different value. That looks like it's 1. So the function is going to 1 as x goes to 2 from the right side. So, okay. So in terms of in general, right? No left side, no right side. In terms of general, what does a limit equal? Well, I don't know. We have two different numbers, right? We have 4 and 1. So I'm not sure which one exactly would it equal. So it's kind of there's a big conceptual t- idea of this. So if we have a left and right limit that are not equal, does a limit exist, right? I don't know. I don't know if it exists. So at the start of the section, we said if f of x goes to some limit L as x goes to A, we write that limit as x approaches A of f of x equals L. So the limits have to be the same coming from the right and left. They have to be the same. And that's actually a big theorem, right? The limit exists if and only if the left equals right. So exists if and only if left equals right. Okay, if they don't equal each other, right? I'll write a different color. So what's it saying is if left doesn't equal right, sorry, then limit as x approaches a of f of x does not exist. D and E does not exist. So if we come back to our example up here, we can see that our left and our right limits don't equal each other, right? 4 does not equal 1. So what this means is that this limit does not exist at 2. Okay? The left and right don't equal each other, does not exist. If they equal each other, it exists. So let's go ahead and check out some examples below here. So for a function whose graph is given, we don't know exactly what it is. State the value of each quantity. If it doesn't exist, explain why. Okay, so if we look at this graph here, we don't really know what it is, right? Let's go ahead and go through these one by one. So for A, this is limit as x approaches 1 of f of x. So what's that limit going to be? So I'm approaching 1, right? Here's 1. What does that limit look like it is? Looks like it's 2. So this limit would just be 2. Okay, so B is limit as x approaches 3 from the left side. Okay, so checking out x approaches 3 from the left side. So I'm coming this way. What does that limit looks like is going to? 3 from the left side. Looks like it's 1. Looks like it's 1. So we'll say limit as x approaches 3 is 1. Okay. So part C is limit as x approaches 3 from the right now, right? So I'm going to check out 3 from the right side. So if we're coming from the right, looks like it's at 4. So this one would be 4 from the right. Okay. So for part D, well, now it's asking what is the limit altogether, right? Does our left limit equal our right limit? Well, no, our left limit is 1 and our right limit is 4. So what does that mean altogether for our limit at 3 is does not exist. I'll make a note like left doesn't equal right. 1 doesn't equal 4. Okay. And lastly, this is part E, f of 3. That's just asking where 3 is actually defined at. And it's actually this solid point right here, f of 3, which is just 3. Okay, so notice how the limits don't matter where x is actually defined at, right? It's just asking about where the graph is going. So that's how you solve these ones. Okay, so now that we have one set of limits down, let's go ahead and move on to infinite limits. Okay, so kind of a new topic, but still in the idea of limits. So infinite limits, Suppose f is defined for all x near a, and so it's saying is if the function grows arbitrarily large for all x sufficiently close to but not equal to a, right? We write the limit as x approaches a of f of x equals infinity. So visually, what this is saying is that, you have some graph, right? You have some a, a value, x equals a. What this is saying is that as it gets really close to a, it's going off to infinity. Okay. So it's never going to equal a, but as it gets close to a, it's shooting off to infinity. And likewise, if f of x gets negative and grows arbitrarily large, as it gets close to a but not equal to, we write as x approaches a, f of x equals negative infinity. So likewise, graphically, it looks something like this. Here you are at a, and you shoot off to negative infinity. You never be equal a. So yeah, in this case, we would say it approaches negative infinity. Okay, so here's a good representation as well. As x approaches a, right? You're going to negative infinity, you're going to negative infinity. Um, and so an infinite limit means the limit itself is infinity, positive or negative. So kind of a question talking about left and right side limits, but what if the function goes to positive infinity from one side and goes to negative infinity when approaching the other? Like this specific function here, 1 over x, that's graphed below. Okay, so what actually is the limit of this guy? So let's kind of piece by piece check this out. So we want to find a limit at 0, right? So let's go ahead and check out the left and right side limits. So limit as x approaches 0 from the left of f of x. Well, you know what? I'll write 1 over x. But what does that equal? So I'm approaching x equals 0 from the left. That means I'm looking at this guy. Well, where am I shooting off to? I'm shooting off to negative infinity. Okay. Now, if we look at the right limit of this guy, coming from the right side, right? Where am I following? I'm going up to positive infinity. I'm shooting all the way up there. So I'm going to positive infinity. So remember, our left and right limits need to equal each other. So altogether, the limit as x approaches 0 of 1 over x, our left and right don't equal each other. One's negative, one's positive infinity. So this is also just does not exist. Okay, just left and right limits don't equal each other. Okay, so this leads us into the topic, which you've heard this phrase before, I assume, is vertical asymptotes. So these limits that go off to negative infinity or infinity when we approach a specific line like x equals a, here with x equals 0, but in general, so this line is called the vertical asymptote. And this is this phrase you probably should have heard in your previous algebra classes. Okay, so let's go ahead and check out more about vertical asymptote. So here's a good definition box, vertical asymptote. So if you're finding a limit at some x approaches a and you're getting positive or negative infinity, and if you're approaching it from the right, you get positive and negative, or you're approaching it from the left and you get positive or negative infinity, then that line x equals a is a vertical asymptote of that function. Okay, so let's look at these examples and see these vertical asymptotes. So this first one is as x approaches 1 of g of x. Okay. So here, I know it's a little hard to see, but here is 1. So as x approaches 1, right, I'm checking out the left side and I'm checking out the right side. They both go off to positive infinity. So the answer to this would just be infinity, right? The left side equals the right side. So I'll kind of make a note like that. Left equals right. Okay. So part B is as x approaches 3 from the left. So now we're checking out this guy. So we're approaching 3 from the left, right? That's coming this way. So that means I'm following the graph and I'm going down to negative infinity. So this would be negative infinity. Okay. So now it's asking, I kind of want to change this question and say, well, what if we approach it from the right? I'm writing like a little, use a different color, little plus there. Okay, that means I'm approaching it from the right. So if I'm approaching it, the function from the right, I'm coming this way. So that means I'm following the graph kind of that way. And where am I going off to? I'm going off to positive infinity, way up there. So this is positive infinity. So now let me ask kind of a new question. As x approaches 3 altogether, right? We'll do my left limit and my right limit equal each other. No, right? One is negative, one is positive. So that means altogether this limit does not exist because, left does not equal right. Okay, so that is, this also tells us that these values, x equals 1 and x equals 3, are vertical asymptotes because we're shooting off to infinities, positive or negative. But okay, so that is for vertical asymptotes and shooting off to infinities. So let's go ahead and just kind of introduce to finding limits in the first place. So finding limits, there's a big property called direct substitution property. So if f is a polynomial or rational function and a is in the domain, meaning you're not getting a 0 on the bottom, not getting 0 on bottom if plug in x equals a, then what you actually can do is actually just plug in a. Plug in x equals a. So if you're not getting a 0 on the bottom, what you can actually do is just plug in a in the first place. So we'll use this fact whenever we can, right? It's always our first option, and we can always just find it directly. We will do that. So key thing here, as I just mentioned, it must be in the domain, meaning you can't get a 0 on the bottom. So I'll say like no, number over 0. I'll say big no, no. That means you're doing it wrong. Okay, so let's try out a couple of these problems. So limit as x approaches 3 of f 4x squared minus 5x plus 7. Will I get a 0 on the bottom here? No, there's not even a bottom denominator really. So I could just plug in x equals 3. So 4 times 3 squared minus 5 times 3 plus 7. Okay, so if I work this out, I get 4 times 9 minus 15 plus 7, 36 minus 15 plus 7, which is just 28. Okay. Let's try the next one. Okay, so x approaches 2, x squared minus 4 over x minus 2. So If I plug in 2, what's going to happen? Well, I'm going to get a 0 on the bottom. So I can't plug in 2. If you plug in 2 and you end up with 0 on the bottom, it's incorrect. Okay, so can't plug in 2, can't have 0 on the bottom. Like, no. So what you got to do is use some algebra. So I noticed that I can factor this top into something. So limit as x approaches 2 of, I can factor x squared minus 4 into x plus 2 and x minus 2 all over x minus 2. And I notice that I can cancel these guys out. So notice how I'm continually writing the limit as x approaches 2. If you don't write that, it will be wrong. Okay, so I have x plus 2 alone. And now can I plug in 2? Yes, because I'm not going to get a 0 on the bottom. It's just not going to happen. So if I plug in 2, now that I plug in 2, the limit goes away. I'm plugging in 2 for x, and I end up with 4. Okay, so last question here. This one's a little more involved, but from our algebra review, you just got to rationalize the numerator. So what you would do here is multiply the top and bottom by 4u plus 1 plus 3, right? And square root of 4u plus 1 plus 3. Okay, so what this becomes is the limit, right? Got to rewrite the limit. U approaches 2, and then the top, when you rationalize the numerator, the square roots go away, and you're left with just these two things being multiplied. So this comes out to 4u plus 1 minus 9. Okay, so that's how the process always works when you rationalize that. Okay, the square root just goes away and you're left with the multiplication of these. So on the bottom, what you have is u minus 2, and I don't even want to multiply all of that out. It's just too ugly. I'm gonna leave it like this, right? I'm not even multiplying those things out. Okay, so that's what I'm left with, and could come simplify a bit. So this becomes coming down here, limit as u approaches 2 of 4u minus 8 over u minus 2 and square root of 4u plus 1 plus 3. Okay, so now we're still simplifying, right? What's one thing these two have in common? 4u minus 8. They have a 2 in common. So what I'm going to do is factor out a 2. So this becomes limit as u approaches 2 of factoring out a 2. This becomes u minus 4. I'm sorry, not a 2. They have a 4 in common. So I have a 4 in common, and so I factor out a 4. This becomes u minus 2 all over u minus 2 times the square root of 4u plus 1 plus 3. Okay, so running out of room a bit, let me kind of add a separate blank page. Okay, so what do I notice about the u minus 2's? They cancel out. I can cancel those guys out. So what I'm left with is limit as u approaches 2 of, I'm going to write the denominator first, 4u plus 1, the square root of that, plus 3 all over 4. So now, is it okay for me to plug in 2? Am I going to get a 0 on the bottom? No way, because there's not even like a minus here that would like cause that issue. So I can just plug in 2 for u. And notice how I kept writing limit all over again. And now the limit's going to go away because I'm actually plugging in 2. So this becomes 4 times 2 plus 1 square root plus 3, and that's all under 4. All right, that simplifies out to 4 over square root of 9 plus 3, which is just 4 over 3 plus 3, which is just 4 over 6, and that reduces down to 2/3. Okay, so that is how you would find the limit of this. And once again, if you can't just direct substitute it, there will be some algebra involved. And if you can't do any algebra, just graph it. But okay, that's it for this video. See you next time.